The sanctions were supposed to freeze China's semiconductor industry somewhere around 14 nanometers. That was the idea. Cut off the EUV machines, isolate the supply chain, protect the technological lead, clean, logical, and on paper completely airtight. Then, in the late summer of 2023, Huawei quietly released a smartphone containing a 7-nanometer processor, not in 2030, but right in the middle of a shifting geopolitical freeze. Which is where this story stops being about a single smartphone and starts becoming something much stranger. To understand why this sent shockwaves through Washington and Eindhoven, have to realize that extreme ultraviolet or EUV lithography systems were treated almost like sacred objects in the chip world. The conventional wisdom was simple. These machines are impossible to replicate without decades of accumulated expertise from Europe, Japan, and the United States. One EUV scanner contains over 100,000 components. It relies on Carl Zeiss optics polished to atomic tolerances, and lasers from Trumpf powerful enough to vaporize microscopic droplets of molten tin 50,000 times per second to create a plasma hotter than the surface of the sun. The mirrors are so unbelievably precise that if you scaled one up to the size of Germany, the largest imperfection would be smaller than a single millimeter. For years, the assumption was comforting. Nobody catches up to this level of physics quickly, especially not under a total blockade. And honestly, that assumption made perfect sense. China couldn't buy the machines. The Dutch government, under US pressure, blocked ASML from exporting EUV systems to Beijing back in 2019. Advanced AI chips followed, then semiconductor manufacturing tools, then electronic design automation software from Cadence and Synopsys. Layer after layer, the strategy wasn't just to slow China down. It was to create technological altitude sickness. The goal was to make the climb so steep and the air so thin that entire industrial sectors would lose oxygen before ever reaching the summit. Instead, something else happened. Faced with a wall, Chinese semiconductor manufacturing firms like SMIC, tech giants like Huawei, and a sprawling network of state-backed research labs began reorganizing around an ugly, liberating realization. If they couldn't buy EUV lithography, they had to attack the problem sideways. Not elegantly, not efficiently, just relentlessly. Hundreds of engineers spread across optics, plasma physics, material science, computational lithography, and advanced chip packaging started solving fragments of the problem independently, intending to stitch them together later. That shift matters more than most people realize because the entire modern tech economy was built on the assumption that extreme specialization protects incumbents. ASML makes the lithography machines. TSMC manufactures the silicon. ARM designs the underlying architecture. Everyone occupies one hyper-efficient layer. China looked at that global structure and effectively asked, what if we blur the layers until the bottlenecks stop functioning? There is a reason Dutch intelligence reports started quietly warning about knowledge transfer networks, instead of just standard hardware leakage. The concern wasn't simply intellectual property theft. It was that Beijing had stopped treating semiconductors as a commercial industry and started treating them like strategic infrastructure, more comparable to a national nuclear program or a space launch capability. That means different incentives, a different definition of profit, and a completely different patience horizon. And there is a detail buried inside a Washington think tank report from late 2024 that almost nobody discussed publicly. As Western sanctions tightened, Chinese semiconductor equipment firms actually saw their domestic procurement rates shoot upward. It sounds completely backwards until you realize that the restrictions did something unexpected. They forced Chinese tech companies to work with imperfect local tools earlier than they ever would have chosen to commercially. It was brutal and painful in the short term, but potentially transformative for their domestic ecosystem later. While Western analysts wrote reports about freezing China's AI future, China responded by graduating more semiconductor engineers than the United States and the European Union combined. Now let's be completely clear here. China has not caught up to ASML in the purest technical sense. Anyone claiming that Beijing secretly cloned a high-end EUV machine in a hidden facility is selling a fantasy. ASML still operates at a level of systems integration that remains extraordinary and unrivaled. But the real issue is subtler, and probably far more dangerous for Western planners. China may not need to fully replicate ASML's exact path to weaken ASML's strategic leverage, because once enough engineering workarounds accumulate, advanced deep ultraviolet multi-patterning, chiplet architectures, AI-assisted yield optimization, domestic chemical vapor deposition tools, indigenous photoresists, the global monopoly stops functioning like an impassable wall. Instead, it starts functioning like a tax. It makes production more expensive and it makes it annoying, but it remains entirely survivable, and this is where a specific, quietly whispered number actually matters. Not because a small group of engineers individually solved EUV lithography. They didn't. The real story is that China rediscovered something the West stopped believing in decades ago. Large-scale industrial coordination still works if a state is willing to absorb financial inefficiency long enough to build competence. The easiest mistake to make is imagining EUV lithography as one impossible invention, a singular breakthrough or a lone moment of genius. It wasn't. It was 30 years of accumulated tolerances stacked on top of each other until the entire system became too complicated to copy, which is exactly why China stopped trying to copy it directly. There's a tendency in Western analysis to frame Chinese technology development as a predictable loop. Imitation followed by massive scaling. You see it in cheap smartphones, faster high-speed trains, and solar panels. Just repeat the formula. But semiconductors broke that model because the bottleneck wasn't manufacturing volume. It was precision physics under brutal industrial conditions. You cannot easily brute force a mirror polished to less than 0.1 nanometers of surface variation. So, Chinese firms changed the battlefield. Instead of obsessing over one perfect, unattainable machine, they started building redundancy around the machine's absence. Multi-patterning with older deep ultraviolet machines became one route. Advanced packaging, where you link smaller chips together to mimic a massive one, became another. AI-assisted defect correction quietly became a third. None of these individual technologies replace an EUV scanner, but together, they reduce dependence on it, just enough to keep the train moving. They didn't beat the sanctions cleanly, they absorbed them, which brings us back to the number 300. To understand how a parallel technological universe is being born, we have to look past the political speeches and narrow the lens down to a single, highly specialized institute in Chengdu, where a specific team was handed a task that technically shouldn't have been possible with the tools they had left on the table. And what they did next reveals the exact flaw in the West's entire containment strategy. To understand exactly what that team in Chengdu was looking at, you have to look at the sheer absurdity of what an EUV machine actually does. In the semiconductor world, making a microchip is essentially an incredibly high-tech game of stenciling. You take a slice of silicon, coat it with a light-sensitive chemical called a photoresist, and shine light through a mask containing the blueprint of the circuit. Where the light hits, the chemical changes, allowing you to etch out microscopic pathways for electricity. For decades, this worked beautifully using deep ultraviolet, or DUV, light with a wavelength of 193 nanometers. But as chips grew smaller, engineers ran into a physical wall. Trying to etch a 7-nanometer feature using a 193-nanometer light wave is like trying to draw a razor-thin line using a fat, fuzzy highlighter. The light is just too blunt for the geometry. The global tech industry spent billions finding a sharper tool, eventually settling on extreme ultraviolet light, which has a wavelength of just 13.5 nanometers. Now you're drawing with a laser-fine scalpel, but here is the catch that everyone missed. 13.5 nanometer light does not exist naturally in a usable form on Earth. In fact, it hates existing. Extreme ultraviolet light is so fragile that it is absorbed by almost everything, including regular air. If you shine an EUV beam through a room, the atmosphere swallows it instantly. So the entire machine has to operate within a massive ultra-high vacuum chamber that is emptier than deep space. Not only that, you cannot use standard glass lenses to focus the light. Why? Because glass absorbs EUV light too. Instead, ASML had to rely on those mind-bogglingly precise mirrors polished by Zeiss, coated with dozens of alternating nanolayers of silicon and molybdenum to subtly bounce the light toward the silicon wafer. So how do you generate this hyper-fragile light in the first place? You drop microscopic droplets of molten tin inside a vacuum chamber. You fire a high-power carbon dioxide laser at each droplet to flatten it, then fire a second, more powerful pulse to vaporize that tin into a screamingly hot plasma. That plasma releases the 13.5 nanometer light. And you have to repeat that process 50,000 times every single second, with absolute precision, without a single microsecond of drift. This is what the West cut China off from. The assumption was that if you don't have the tin droplet generator, the vacuum systems, and the Zeiss mirrors, you are stuck in the technological Stone Age. Your highlighter remains fat and your lines remain blurry. But remember, China decided to attack the problem sideways. If you cannot get the ultra-sharp scalpel, you have to figure out a way to draw ultra-thin lines using the fat highlighter you already own. This is where the Institute of Optics and Electronics in Chengdu, alongside teams from Tsinghua University, stepped in with a technique known as DUV multi-patterning. It is a process that sounds completely unhinged to anyone concerned with manufacturing efficiency, but it works. Imagine you want to draw two parallel lines that are incredibly close together, closer than your fat highlighter can manage in a single stroke. If you try to draw them at the same time, the ink bleeds together into one big mess. So, instead of drawing them together, you draw the first line. Then you put down a protective hard mask over that line. Then you wash the wafer, reset the machine, shift the entire silicon wafer by just a few nanometers with terrifying precision, and draw the second line right next to the first one. You are effectively splitting a single, complex layer of a chip into 2, 3, or even 4 separate printing steps using older DUV machinery. It is called quadruple patterning, and it is the exact technical wizardry SMIC used to extract that 7-nanometer Kirin chip out of machines that were never designed to go below 14 nanometers. But here is the part that most people don't realize. Multi-patterning comes with a mass compounding penalty. Every time you add an exposure step, you introduce a new opportunity for alignment errors, known in the industry as overlay drift. If your silicon wafer shifts by even the width of a single atom out of place during the third print, the entire circuit short-circuits. It is dead silicon. In a standard commercial fab like TSMC, the goal is high yield, meaning 80 to 90% of the chips on a wafer come out working perfectly. This keeps costs low and profits high. With DUV multi-patterning at advanced nodes, your yield plummets. Some industry insiders estimated that China's early 7-nanometer yields were well below 40%. For a Western company answerable to Wall Street shareholders, that is a fast track to bankruptcy. You are throwing more than half your expensive raw materials directly into the trash. But as we established, Beijing wasn't playing a commercial game. They were playing a survival game. If a state fund is paying for the wasted silicon, a 30% yield still means you are getting functional 7-nanometer chips for your domestic infrastructure. Yet, relying purely on state cash to absorb waste isn't a permanent strategy. You eventually run out of runway. The engineers knew they had to stabilize the system, but they couldn't magically make the older DUV hardware more precise. So they turned to an invisible savior, computational lithography, instead of demanding impossible physical perfection from the hardware. Chinese software engineers began writing massive algorithmic models that predict exactly how the light will distort and bleed when it hits the photoresist through an older lens. Think of it like active noise-canceling headphones, but for light waves. Before the DUV machine fires, the software intentionally distorts the mask pattern in reverse. When the distorted light passes through the imperfect tool, it cancels out the physical errors and lands on the silicon in a perfectly sharp, ultra-thin line. They began using sheer compute power to compensate for missing hardware tolerances. They changed the rules of the ecosystem. And right as Western planners realized that multi-patterning and software fixes were keeping China moving, the story took an even more unexpected turn. Because while everyone was looking down at the microscopic lines on the silicon wafers, Chinese designers started looking up. They realized that printing smaller transistors wasn't the only way to build a faster brain, which brings us to a completely different engineering, Frontier 1, that turns a single massive manufacturing bottleneck into a logistics problem that can be solved across multiple factories. That frontier is something called advanced packaging, and it represents a massive shift in how the tech world defines progress. For 50 years, the semiconductor industry followed a single comforting rule known as Moore's Law. The number of transistors on a microchip doubles roughly every 2 years by shrinking them down physically. It was a race toward the microscopic, but as shrinking those transistors becomes absurdly expensive and physically blocked by atomic limits, the industry has stumbled upon a simpler question. If you can't easily build one giant perfect brain, why not stitch smaller brains together so seamlessly that they act like one? This is the world of chiplets. Instead of manufacturing a single massive silicon die that handles everything from logic to memory, you break the design apart. You manufacture the logic component on a complex node, create the memory on an older, cheaper node, and then link them together on a high-tech silicon bridge. For China, this was the ultimate strategic escape hatch. If their domestic fabs could only produce 7-nanometer chips at low yields, they could take those precious components, combine them with older 14-nanometer or 28-nanometer blocks, and wrap them in an advanced package. The final product might look like a single high-performance AI processor to the outside world, but underneath, it is a mosaic of different generations of technology working in tandem. And that is where the West's entire containment model truly began to fracture. The strategy behind the export controls was inherently linear. It viewed the semiconductor industry like an assembly line. If you remove a critical piece of machinery from the middle of the line, the whole factory grinds to a halt. It was a beautiful static theory, but an engineering ecosystem under extreme pressure behaves less like a static factory and more like a biological system. When you block one artery, the body doesn't just give up. It slowly forces blood through smaller, auxiliary vessels, expanding them until they can handle the load. There is a powerful historical irony playing out here that most people completely miss. For the last 30 years, hyperglobalization optimized the technology sector for absolute efficiency. The entire planet shared a single razor-thin supply chain. A chemical would be synthesized in Japan, shipped to Taiwan for wafer fabrication, sent to Malaysia for packaging, using design software written in California, powered by a machine built in the Netherlands. It was a masterpiece of capitalism. It kept your smartphones cheap and corporate profit margins historically high, but hyper-efficiency is the mortal enemy of resilience. By removing all redundancy from the system to chase maximum profit, the global tech sector created a world where a single political decision in Washington or a supply chain choke point in Europe could paralyze global industries. When the United States weaponized that fragility to lock China out of the network, they assumed isolation would compound Beijing's weakness. In reality, it compounded their motivation. Before 2019, if you were a Chinese smartphone maker or a local cloud computing giant, you had absolutely no commercial reason to buy a Chinese-made lithography tool or a local photoresist chemical. The Western and Japanese alternatives were simply better, more reliable, and cheaper. Buying domestic was a bad business decision. But the moment the sanctions dropped, preference stopped mattering. Surviving mattered. Suddenly, obscure Chinese equipment makers, who had been laboring in obscurity for 20 years, found themselves with a line of desperate domestic customers outside their door. They were handed billions in state capital, but more importantly, they were given real-world deployment data under immense pressure. In engineering, there is no substitute for failure. You can simulate a clean room in a university lab for a decade, but you won't truly understand how your chemical or your optics module behaves until a massive factory runs it 24 hours a day until it breaks. Sanctions forced that brutal learning curve to compress at a speed that shocked Western observers. Which brings us back to the warning given by former ASML CEO Peter Wennink. He wasn't speaking out of a sense of corporate greed or political alignment when he warned that cutting off China would push them to self-sufficiency. He was simply stating an unyielding law of industrial gravity. If you create a massive, vacuously empty space in a market containing 1.4 billion people and endless capital, that vacuum will eventually pull in resources until it fills itself. So where does this leave the balance of technological power? The strange, uncomfortable reality is that the semiconductor world is quietly fracturing into two completely parallel tech ecosystems that no longer speak the same language or share the same goals. On one side, you have the Western-aligned stack, anchored by ASML, TSMC, and NVIDIA. This ecosystem is optimized for the absolute frontier of technical performance, pushing toward 2-nanometer nodes and beyond, regardless of how fragile or geopolitically tense the geography of Taiwan becomes. It is a system built for the peak of efficiency. On the other side, you have the emerging Chinese domestic stack. It is messy, it is inefficient, and it relies on complex software, chiplet packaging, and multi-patterning workarounds to achieve what the West does with a single flash of an EUV laser. It is a system built not for efficiency, but for absolute, unconditional survivability under siege. The mistake Western planners made was believing that because China's methods were less elegant, they were a failure. They mistook attacks for a wall. China is absolutely paying a massive premium in energy, capital, and wasted silicon to build their chips, but they are building them, and in a geopolitical chess match, a working sovereign 7 nanometer or 5 nanometer chip that cannot be shut off by a foreign power is worth infinitely more than a theoretical 2 nanometer design sitting on a restricted server in Silicon Valley. And yet, this parallel evolution leaves one massive unresolved paradox at the center of the global economy. Because while China has managed to bypass the immediate wall of the 14 nanometer freeze, they are now approaching an entirely new set of physical limits where workarounds, packaging tricks, and software optimization can no longer bridge the gap. They are running out of clever ways to cheat the physics of light, which means the true crisis isn't behind us. It is looming right on the horizon, at a hidden choke point that neither Washington nor Beijing has figured out how to control. That hidden choke point isn't even about the lithography machines anymore. It is about something far more fundamental to the physical universe: energy and materials. As you push these older deep ultraviolet systems to print layers 4 times over, as you pack clusters of mismatched chiplets together on complex silicon bridges, your power requirements don't just increase, they spike exponentially. A computing architecture built on workarounds is inherently hungry. It runs hotter, it requires massive AI-driven cooling infrastructure, and it demands exotic, ultra-pure chemical photoresists that are notoriously difficult to synthesize at scale without global supply lines. China has proven it can survive the initial altitude sickness of the technology blockade. It has successfully industrialized an alternative path. But the laws of physics are not a political opponent. They cannot be negotiated with. And they cannot be bypassed through sheer state administrative endurance forever. Which brings us back to the central irony of this entire global saga. By attempting to freeze China's semiconductor capability at an arbitrary line in the sand, the West inadvertently triggered the exact industrial transformation it spent a generation trying to prevent. Before the sanctions, the globalized supply chain was Washington's greatest leverage point. It was a golden handcuff system where every player was too dependent on the others to ever risk breaking the machine. By unlocking those handcuffs, the sanctions forced a massive nuclear-scale tech economy to learn how to walk on its own 2 feet. The strategy was designed to protect a permanent moat. Instead, it built a competitor that no longer fears the moat because it has learned how to build its own castles. So, what does the future actually look like? We are not entering a world where China cleanly catches up and copies ASML's highest-end machines to create a perfect mirror image of Western technology. That is a simplistic view. Instead, we are entering a much darker, more unpredictable era of technological fragmentation. The next decade won't be defined by who has the fastest processor in a commercial laboratory. It will be defined by which system can withstand the most pressure when the global fabric of trade truly begins to unravel. If you look closely at the numbers, the true victory for Beijing wasn't the release of a single smartphone in 2023, or the scaling of a low-yield 7-nanometer factory line. The true victory was psychological. The moment a generation of Chinese engineers, students, and policymakers stopped viewing Western technology as a permanent foundation and started viewing it as a hostile vulnerability, the timeline changed forever. When you look at a modern microchip, it is easy to see it as a triumph of pure human intellect, a collection of billions of microscopic gates acting as a testament to what civilization can achieve when it optimizes for absolute perfection. But the story of the semiconductor blockade reveals a different truth entirely. Technology is never just about the pure science. It is an expression of human organization, political will, and the raw instinct to survive under constraint. The 300 engineers working across those overlapping labs in Chengdu and Shanghai didn't need to clone the world's most sophisticated machine to shift the balance of geopolitical power. They just needed to prove that the machine's monopoly was an illusion. They cracked the unwritten rule that says only one specific, globalized system is allowed to define the future of computing. And as the semiconductor stack splits into 2 separate worlds, one chasing the absolute limits of efficiency, and the other fortifying itself for absolute resilience, the rest of the global economy is left watching an incredibly uncomfortable experiment play out in real time. We are about to find out what happens when the most complex industry in human history stops being driven by the pursuit of profit and starts being driven by the cold, calculated logic of sovereign survival. The sanctions were supposed to freeze a country in time. Instead, they act as a catalyst, accelerating an industrial evolution that is quietly rewriting the rules of the modern world. The West built a machine so advanced that its mirrors could detect an imperfection smaller than a virus, believing that level of precision would guarantee a permanent empire. But they forgot a basic rule of human history. A wall only works if the person on the other side believes there is no other way to climb. Once that belief disappears, the wall is just an expensive pile of rocks. The next phase of this struggle won't be fought in the clean rooms of Eindhoven or the boardrooms of Silicon Valley. It is already unfolding inside the server racks of massive data centers, down in the deep-sea shipping lanes, and across the narrow waters of the Taiwan Strait. And the strange part isn't how many variables are now out of control. It's how predictably they all fell into place the moment we stopped looking at the technology and started looking at the human desperation underneath.